Hey people, hope you're doing great. Here we are, 3-2. We are on page 166 for examples 1 and 2 and 3. So we're still going to be doing functions. We're going to see some different kinds of functions today, maybe linear ones and nonlinear ones. We're going to be writing functions.
Nonlinear?
Yeah, so we're going to give you some hints there. In the meantime, let's hop right into it. Here we go. Hopefully we got volume.
What are different representations of a function? Think about this question during the lesson.
Tables, graphs.
A 10,000 gallon swimming pool needs to be emptied. 2,000 gallons have already been pumped out of the pool and into the tanker. You can tell from the diagram that the pump moves 720 gallons of water per hour.
How
How can you determine how long it will take to pump all of the water into the tanker? How to use what you know about linear equations to solve the problem?
Well, we could probably write an equation. Guys, that's what we've been doing. So 2,000 gallons so far, there's that starting quantity, that initial value. 720 gallons per hour. Per hour, there's your rate of change or your slope, right? Write me an equation in slope-intercept form. Y equals mx plus b, guys. There's your slope, there's your y-intercept. Right? This is, look, we should be okay here.
One way is to draw a diagram that represents the situation. Then write an equation.
Bar
The top
diagrams,
bar
we've seen this
represents the
before.
total amount of water to be pumped from the pool.
Yep, 10,000 gallons.
The first bottom bar represents the amount of water already pumped. The initial value, or y-intercept, 2,000 gallons.
Yep.
Each additional box represents the amount of water pumped per hour. The constant rate of change, or slope, 720 gallons per hour. We need to determine H, the number of hours needed to pump the remaining water. Which equation does the diagram represent?
Select your answer.
Well, remember, we talked about, guys, 720, right, gallons per hour. There's your slope. We know that's going to have our variable. Look, they didn't use x and y here, but we should be able to figure this one out. So 10,000 gallons, right, is one bar. That has to be equal to the other bars here. So I don't think we want to equal 720. Ooh, maybe it's this one. 10,000 equals 2,000 H plus 720. No, remember, 2,000 is our constant. So, no, we're not going to be equal to 2,000. I think it's this one down here. But I like to hear that sound. So let's pick this one. Oh, okay.
I love that sound.
You can now solve this equation to find how long it will take to pump all the water into the tanker.
There we go. Yes, we can. And you could have solved that equation too. But it was
Another
right
way to solve the problem is to use the information given to make a graph.
Make a
In
graph.
this graph, the y-axis shows the water pumped in gallons, and the x-axis shows time in hours.
Yep.
Let's plot some data points.
Select your answer.
Think about where this graph is going to start, guys. Where is the point that represents the initial value? Was my initial value 0, 2,000, or 10,000?
Didn't they already pump out 2,000 gallons?
Yeah, they already pumped out 2,000. That's
Your
why we're going
initial
to start
value
there.
is 2,000 gallons. You know that you can pump 720 gallons each hour.
Each hour.
Now draw a line through the data points. The line has a slope of 720.
That makes
It's
sense.
a straight line, so it's a linear function. The total water that needs to be pumped is 10,000 gallons. You could extend the line to find the value of x when y is 10,000. Now you know how to represent a linear function using a bar diagram, an equation, and a graph.
That's right. Yes, we do. Now it's our turn to do something. As the pump is pumping water, the amount of water in the pool decreases, right? That makes sense. 720 gallons go out every hour. Complete the statement below, then graph the function. Ooh. The amount of water remaining in the pool is blank gallons. The amount of water pumped each hour is blank gallons. The equation is blank. Okay. Do we know how much water is in this pool, guys? Do we? Do we know? Well, remember, It had 10,000 gallons in it, but how much was already out of it? 8,000 gallons, yes.
8,000.
Okay. So the amount of water remaining in the pool is 8,000 gallons. The amount of water pumped each hour, right? How much water were we pumping each hour? Is that going to change? No, we're still pumping 720 gallons, right? The equation is, okay. All right, now think about this, guys. This is a little bit of a different scenario, right? We're talking about the water that's in the pool, and it's decreasing, right? We're not worried about the truck where the water's going into, so now we're in the pool. Think about, so the water in the pool started at 8,000, and every hour that goes by, right after the first hour, how much water is left in there? Well, whatever 8,000 minus 720 is, because that's how much water we're pumping out every hour. And then another hour goes by, and we lose another 720 gallons. So think about, like, when we go to graph this, what kind of slope is that going to have on our graph? Well, let's before we write the equation, let's just kind of think about it. So we know if we're going to graph it, guys, here's my starting value, my initial quantity, my y-intercept, 8,000. So let's find 8,000 on this graph. And let's, of course, why wouldn't we be counting by thousands here? So let's see, we're, 1,500, this is ridiculous, 750. Who's to say, guys? I'm going to say we're going to start right about here. Okay? You guys okay with that?
Yep.
Why not? Okay, now every hour that goes by, there's less water in the pool by 720 gallons. So if we think about it, if we had 8,000 gallons, right, we're going to go down 720. So Mr. Noel's going to have to help me out. That's 7,250, or no, 7,280.
Yeah. Well, let's go over to 10 hours. Could we do that?
10 hours?
Yeah. Because 10 hours a time would pump out 7,200 gallons.
Yes, it would.
So that would mean how much would be left after 10 hours?
80 gallons.
800 gallons.
800 gallons. Which
Could we
still
go-
isn't, that's still not a good number,
Still
though.
not a good one.
Because this is only 750. I know.
Terrible scale.
It is a 10. We should make a better scale when we do this. Anyway, so guys, let's write our equation here. So our equation, we're going to write it in slope-intercept form because that's what we've been doing. So y is the amount of water in pool. So that is equal to, what's our slope here? Well, our slope was 720, but remember, this line, guys, is going to go downhill. So what kind of slope is that? That's negative. So I have to be a negative 720 gallons, right? And where did we start? Well, we started at 8,000. So if we want to graph this, guys, here, let's just say every 2 hours that go by, we should go down 1,440 gallons, right? So let's just say that is about here, right? And it can follow that same, pattern of about here, and who's to say? Something like that, okay? Again, maybe we'll make better numbers in class so it works out better, but guys, what we're really concerned with is writing a function to model this scenario. When we get to the graphing part, we all know that that's the fun part. Okay, I think we're good there. Example 2.
Let's go to example 2.
What do you got?
Hopefully it's better.
Yeah.
Oh, I think we got to talk about
How can you determine whether the relationship between side length and area is a function?
Okay, so we're still talking about are things a function, all right? So, guys, let's just do what we did the other day. Look at all of your x values, right? Here's a table. Okay, so study that table. Ask yourself, is that a function? Does every input, each input, have exactly one output? Absolutely, yes. We have no repeating x values here, so we can confirm that this is indeed a function. You guys go with that? Now, I'm not going to give away the secret just yet. Yes, so the relationship is a function. There we go. And everything just went away? Oh, here we go. I got you guys. Okay, so they've graphed it. Notice, guys, have we seen these kinds of lines before?
No.
No. Do you think this is a linear function?
No.
Mm-mm. No, guys, when we see curves, right, lines that make a curve, right, these are what we call nonlinear functions. This is what they look like on a graph. This is what they look like on a table. And focus your attention back over here. If we only had the table, how would we figure out if it was nonlinear? I'm glad you asked. So, again, carefully look at these x values. Is there a pattern in my x values? Sure there is, right? We're just going up by 1 each time. What are we going up by in these y values, we'll call them? When we go 0 to 1, okay, that went up by 1. Then we go from 1 to 4, it went up by 3. And then 4 to 9 goes up by 5. 9 to 16 goes up by 7. 16 to 25 goes up by 9. So are they going up by the same number each time?
No.
No. And that's a dead giveaway, guys, for yes, this is still a function, but it's not going to be a linear function like we've seen. So it's not going to make a straight line on a graph. It's going to make this curved line here.
Does not go at a constant rate.
So I can easily figure that out, guys. Just do a little bit of subtraction. You know what I mean? To figure out what your difference is between all of these. And if it's the same number, we know it's going to be linear. If it's not, then it won't be. Okay? So guys, there's nonlinear stuff. Okay? So we can see it on a table. We should be able to figure out if it's linear or nonlinear. Here's what it looks like on a graph. Still a function though. Okay? You're going to love example 3 because it's probably my favorite out of all these. Okay.
Determine whether each graph represents a function.
All right, so we got all kinds of stuff going on here. So we have some different kinds of functions that we'll see in our different math careers as we go on with life. It says determine if it is a function. And guys, we have a test, a very simple test that we call the vertical line test. And all we have to do is apply this test to these 3 graphs, and then we will know if they're a function. All right?
I love the vertical line test.
Yeah. All right. So this one says the graph represents a function because each x value corresponds to exactly one y value, and I would agree with that. All right, let's see what it says about this one. This one says this one is a function too. All right, because again, each x value has exactly one y value. But this little fellow over here, not so much. Nope, this one doesn't, because think about, guys, we find x values along this axis, right? Each x value, in this case, if you look right here, this x value, which is -2, has 2 different outputs. Right here it's at a 1, and then here it's at a 1, 2, 3, 4, 5. All right, so we don't have we don't have exactly one output, we have 2 outputs here. So this one's not a function. Now, I know you're excited about that vertical line test I was telling you about. Here's how it works, and we're going to do it on all 3 of these. Again, we already know function, function, not a function. Here's how it works. You're going to draw as many vertical lines as you can that go through your function. If your vertical line only goes through it one time, then it gets to be a function. So in other words, guys, I could draw a vertical line right here. Only goes through one time. I could draw another vertical line right here. It still only goes through the function one time. And I could draw one here. Same thing, guys. I could draw as many vertical lines through this function as I want. All of these vertical lines only go through one time. And that's how our test works. If it only goes through once, good to go, you're a function, right? You can kind of envision, right? We can actually use all the little lines that are already on our graph if we wanted to, but maybe you don't like that because, you want to do your own stuff and you want to draw lines wherever you want. Got it? So again, guys, I can draw vertical lines all throughout this function. Still, it only goes through one spot. You can see what's going to happen on this one here. If I draw a line right here, right? How many times did my line go through that so-called graph or function? Well, it goes through twice.
Definitely, more than once.
Okay, and this is how we know, hey, you have failed the vertical line test, right? It fails nearly everywhere on this graph, okay? So this one does not pass the test. As soon as we find one line, just one line, where it goes through the graph twice, it fails the test, and it's not a function, okay? So that's how they came up with not a function, function, and a function there. All right, let's get rid of that. Draw a graph that represents a linear function. Sure, we can do that. What equation represents it? Okay, let's do this one. So I'm going to go right here, and we'll go right here, and over here. No, that's not a great point. We're going to go right here. Okay. So there you go, guys. If you want to ponder that one real quickly, you can. So find the slope, find the y-intercept, put it all together. So go ahead and pause this video, and then do that. When you come back, like magic, I'll have the equation on there. Okay. There you go, guys. This is y equals 1/3 x plus 1. Is this a function?
Yes.
It sure is. It sure is. Okay. Guys, real quickly, because I got a graph and I love to draw. Can you tell me if this is a function? So let's go. Here we go. Function like that. What do you guys think? Function, not a function. Think about that vertical line test. Draw all those little vertical lines in there. If you said function, you got this one right. Nicely
Function.
done. You guys want another one? Okay.
Yes. One more.
One more. Okay. Yes.
Whoa.
There we go. How about that one? Function, not a function. This one is a function too. Good guess there, guys. So yeah, again, we can draw our vertical lines everywhere. They're just going to go through one spot. Okay? All good there. So anyway, so guys, now I think we're ready for our key concepts. They'll be on page 168, I do believe. See you there.